This is about 3-hour tutorial on various aspects of databases. But it's not only databases. As you'll see, as soon as we start looking a bit deeper under the curtain of what database problems are, you will see that they in fact become problems in AI and in other fields of computer science. And in fact, to some extent, some of the work we will discuss today, you can see it also in context of graphical models and so on and so forth. It is called From Joins to Aggregates and Optimization Problems. The idea being that we use a principled approach to solve effectively some of these challenges. Some of them are database challenges, some others are actually, for instance, optimization problems. My name is Dan Olteanu. I'm a professor in computer science at Oxford, and I'm also a Turing Fellow part-time. The slide deck, well, I had to work on it until the very last minute, so I couldn't share it with you before the lecture. But if you go to this website, FDB Research, GitHub.io, under talks, you'll find a link to the PDF. And from there, you can actually get also some of the things that I will perhaps not cover in full today. Right, so before we start, I would like to acknowledge a huge relatively large number of people with whom I worked and who also share slides with me. So this presentation is based on their work as well. In particular, the FDB group at Oxford, made by Zavodny, Schleich, Kara, Ciucanu, myself, collaborators from Relational AI and from Logic Blocks, Abo Kamis and Go, and from Michigan, Nguyen, and some of the slides come also from them. And well, I would like to really thank them for the support and for sharing their work. Good, so what is the actual goal of this tutorial? Usually when you think about databases, you might think about something extremely boring, something that may be required, but is in any way the kind of sparkle, in your research. So that may be, for introductory course on databases that will teach you things done, 4 decades ago, right? Today, however, we try to discuss about a principled, relatively new approach to in-database computation. And by this, I mean not only doing queries inside the database, but doing some other tasks as well. It is relatively new. In any case, it is not mainstream in the sense that there are relatively few database management systems out there that actually picked up yet on this. This is for various reasons. It's not necessarily that this is not exciting, but sometimes it's very difficult, to just go back and redesign things. But you will see that there are actually perhaps good reasons for new startups to use some of these principles. And in fact, this was the case for at least 2 of them. Essentially, the tutorial starts where a mainstream introductory or advanced course on databases finish. The courses, for instance, I will give at Oxford, they talk about the fundamentals, the basics. Here, we actually start from there after we finish that course. And it is principled in the sense that I will not really slave about how to improve a constant factor in performance of a system, which is also great. It is fantastic, and we actually actively work on that thing as well. But rather, I will try to give you some new algorithms that actually have provable better complexities, asymptotic complexities, than the existing approaches you see out there. And in particular, when we talk about joins in the database landscape, one important thing is that the way you construct so-called strategies or execution plans for queries, where you do a join at a time, you join 2 relations, then you produce an output that may be pipelined or may be stored, and then you join that with the next relation, and so on and so forth. That one turned out to be suboptimal, right, for various reasons. And by suboptimality here, I mean that its complexity is actually can be probably higher than the complexity of what actually should be. So we will look now at such things, and then we will see that we can actually do better. And then we'll also tackle on a very important aspect, namely that in databases, usually data is highly redundant. And if you would start representing the data the way we do it at the moment, relationally, record by record, then we may actually entail a huge amount of redundancy, which may be avoided without actually necessarily relying on lossy compression. So we can losslessly compress data, and we can obtain orders of magnitude, basically smaller data sets on which we can still work efficiently afterwards. And what can we do then on top of these representations? Well, we can do aggregates. This is a kind of very important operator in databases where you sum over things, you count. This is also underlying loads of applications out there, and in particular, machine learning, if you want to do it inside the database. So we generalize these algorithms from joins to aggregates over joins. Then we look at a particular framework, formalism, which has been developed rather recently, but has ancestors in the past in AI. It's called functional aggregate queries. It's a formalism that allows you to specify lots of problems that go across databases, logic, probabilistic graphical models, and matrix chain computation. And then we will see how we can effectively solve all these problems using the same approach, the same algorithm that works on the same syntax. And that gives us, again, low computational complexity. And then at the end, we go further, and then we look at optimization problems. In particular, we look at how we could learn regression and classification models inside the database. One observation here is that we like to do it inside the database simply because we want to move the code and not the data, right? Pushing the data outside the database, then inside, a statistical package actually hurts a lot in terms of performance. However, what we like to do is to actually move the code that is for learning regression inside the database engine, and then we can also observe that this code can be rephrased, or let's say the data-dependent part of it could be rephrased so that it becomes actually, a bunch of functional aggregate queries, which we know how to optimize and evaluate efficiently inside the database. For the Turing folks, there are quizzes at the end of the slides. If you like to test your understanding, I'll be very happy if you do that, and then you can send me your solutions and we can discuss about them. They should be fairly okay. I would say that there is nothing challenging that goes beyond what I will try to teach here. And in case you get excited about this, then it may be one way to go ahead. We also obviously want to work with people if they feel this is interesting to them. So let me first start our discussion about joins. They obviously are the basic building block of a query language and of a database management system. Essentially, a join brings together information from various sources, right? So we need that sort of ability in a query language. And because of that, they are studied extensively. However, to our dismay, perhaps, it is only very recently that people discovered that existing approaches out there were suboptimal. And we will actually talk about some of this. Likewise, it lacked a systematic investigation of redundancy in the computation of such joins and also in the representation of their results. And this is what we are going to do in this part, right? Look at this aspect, and you will see there are some very simple algorithms that could be devised to actually overcome the problem. So for part one, I will just introduce very briefly join queries via examples. Then we will look at size bounds for results of queries. The idea here is that if we look at the program, in this case at the query, right, we may actually gain lots of information, lots of structure about how the result would look like, right? So that is actually the cornerstone of, in general, database query optimization. You take advantage of the schema you are given of the database. You take advantage of various sorts of constraints, dependencies that actually hold on the data. And you also take advantage of the query. You look at the query, the query puts together these tables in a certain way. And that can tell you something about the way the result looks like. Okay? In particular, in the query result, the joins introduce so-called join dependencies. No wonder, right? There are some dependencies between blocks of data from the input that will manifest themselves in the result. Another word, let's say another keyword for join dependency would be conditional independence, which you may be more familiar with in other contexts, right? So here the idea is to take advantage of this information that you are given about the data, about the structure. Okay? So you don't assume that the data is just some plain input table and you work on that input table. But because that input table perhaps was generated in a certain way, and if you know that, you can actually do processing on that table much, much faster. Okay? Now, obviously, a research topic here would be how we can go beyond just the query language and look at general programming languages, right? And see, in case they work over tables, how you can take advantage of that. So because of that, first we will have to understand how to capture syntactically and semantically this sort of structure, right? And for that, perhaps the first part may be a bit too theoretical and a little dry, perhaps. But the motivation is clear, right? We need a way to express the information we can gain from the query and from the data, yeah, so that we can then use it to devise efficient algorithms. And first of all, before we do the actual algorithms to compute join results, we first look at characterization of size bounds for such join queries, right? What does it mean, size bounds? Well, we want to understand, in worst case, what would be the size, how many records would be in the result of that query, yeah? Can you do it better? What if you represent the result in a more succinct way? Can you actually get a better, a smaller size? And for that, we look at the listing representation, which is the standard representation, record by record. And we look also at a more succinct representation, which is factorized in the sense that if you have values in common across records, you might want to factor them out and represent them once. Yeah, so that's the whole idea. And then after we have this information on the bounds, we can then look at the worst case optimal joins. In particular, there is one algorithm which I also teach actually in my advanced class, is the leapfrog try-join, which is one of the first worst case optimal join algorithms. In fact, the first one used in a commercial setting. And then we look at another tool called FDB for factorized databases, where we essentially generalize this to more succinct representations. Good, so introduction to join queries. A very, very simple example is this one. We have 3 tables, orders, dish, and items, right? As you can see, orders, this table has 3 columns, customer, day, and dish. Then that dish column also appears in the dish attribute appears also in the dish table. And this is the way you could express a natural join, right? If you have columns with the same name, when you actually join them, this means that you are looking for values that are the same in both tables. So in this case, we have, I'm not sure whether this works, but well, we'll have here, burger appearing here and there. This means that all the tuples, all the records from the first table that have the dished burger will be joined with all the records from the second table that have the dish burger as well. And then we continue, and then we have hot dog here joined with hot dog there, okay? So in a sense, a join is nothing more than a union of little Cartesian products, maybe little or maybe more, larger, right? In this case, we just pair the first 2 records with the first 3 records, and the last 2 records here with the last 3 records in the second table. And that is to join the first 2 tables. If we want to join in also the third table, we realize that the third table items has 2 columns, item and price, and item, right, appears also in the dish. So we will join then on the item, okay? Which means that all the records that we constructed by joining orders and dish now will be expanded with information about the items, yeah, and prices. And that's all. And then, the natural join would be a relation like that, right? And as you can see already, if you look record by record, there is a lot of repetition. And this is because of these Cartesian products that appear there, right, in the way you do the join, okay? But that's the way we actually work with at the moment, right? Standard relational databases would produce something like that, maybe very large. It may not necessarily store it, but produce, one tuple at a time, one record at a time, so you can do something with the record. Good. A second example is this one. So this is a bit, perhaps, more interesting. It's, we are given, in fact, 3 tables. In fact, all 3 could be, in fact, the same table, and then the join of them would be a self-join called, right, where we join a table with itself on some of the columns. And what we do, we actually join R1, R2, and R3, but as you can see, we join R1 and R2 on the column A, and when we join back also R3 into this mix, then R3 will join with R1 on B, and with R2 on C, right? So this, in fact, is a triangle. If you depict, you know, in your head this join query, you have basically three attributes, three columns, A, B, and C, right? And AB would be covered by R1, AC would be covered by A2, and BC by R3. So it's a clique, in a sense, in this case. It's a special triangle, right? And that, you know, with this, if you have social data, for instance, as input, you would like to compute, you know, whether you have such triangles in your graph, right? Such as, you know, there is a friend of a friend of a friend, right? And they are all friends together somehow, okay? And you can imagine, you know, more interesting social queries about, you know, a degree of separation, you know, paths, you know, and so on and so forth. In this particular case, what's quite interesting is that, you know, if we join the first two, then A0 here appears n plus 1 times, A0 appears in the second table n plus 1 times, and then we get a blow up, right? Only for A0 we get n plus 1 square combinations. It is only later that R3 tells us that not all of these combinations between B's and C's are in fact okay. Yeah? Some of them should be completely discarded. And this is where actually the pitfalls of existing techniques is, right? The fact that, you know, if you join two tables, you may construct a larger intermediate result than the final result. Yeah? You come only later with relation R3 as a patch, as an additional constraint to filter out some of the combinations produced by joining R1 and R2, right? Instead, new algorithms try to look at joining all three relations at the same time, and thereby they avoid this large intermediate result. In fact, if we join here R1 and R2 first, or any of them, R1, R3, or R2, R3, we will see that we can get actually quadratic in M, intermediate representation, and only later when we join R3 or the other remaining relation, we get linear size result, right? If we join all three of them, perhaps we avoid that blow up at the intermediate step, and we can get a linear time algorithm. In general, you know, depending on the data, that algorithm may not be linear time, but as we will see, it will be something like n to the power of 3 over 2, so 1.5. So it's between 1 and 2. It's between linear and quadratic, in fact, you know, in worst case. Okay? Whereas existing approaches will actually take quadratic time, regardless, you know, for the data. Good. So now let us actually reason about the structure we have in the query. And here we introduce certain notions that may appear, you know, in other fields, not only databases, but in databases we call them hypergraphs. And for every join query, we look at a hypergraph of it. What do I mean by a hypergraph? For every variable we have in the query, you construct a node, right? And for every relation symbol we have in the query, we construct a hyperedge. Why is it a hyperedge and not an edge? Well, for the reason that a relation symbol may have several nodes, right? Several variables, right? So it's not just a relationship between two guys, but it's a relationship between potentially n variables, okay? So for instance, in case of the triangle query, this is easy. We have only binary relations. So we have A, B, and C as the nodes, and the hyperedges would be R1 going over AB, R2 going over AC, and R3 going over BC. So the actual nodes would be A, B, C, and the hyperedges are just you know, sets of variables A, B, AC, BC. Okay? Okay. So that's the hypergraph. And that captures somehow, to some extent, the degree of hardness of the query. There has been a lot of work done, you know, something like 30 years ago, on understanding, you know, whether, you know, certain graphs can lead to certain complexities for evaluation of the query. And in particular, this is a so-called cyclic query, right? Because as you can see, there is a cycle, right? Acyclic queries are notoriously simpler. In these queries, you don't have really cycles, right? Or if there is a cycle, in fact, that is subsumed by a larger relation containing all the nodes in that cycle. Okay? So this is a cyclic query. For our example with the order query, right? We have the We have how many variables? Well, we have customer, day, dish, item, and price. We can depict them like this, and then after that, the hyperedges would be, for relation orders would be dish, day, and customer. So now you see a ternary relation, right? So we have an edge which is actually going over 3 nodes and not only over 2. And then the others are binary relations, so we go actually over 2 variables each. Is this clear? Yeah? Okay. So ideally, our hypergraph should actually be a tree, right? This one here was a tree. If it is a tree, you can perhaps intuitively think how you could actually evaluate the query. You can, for instance, go top-down or bottom-up, and you start reducing. You aggregate away price. You aggregate away customer day. Then you aggregate away item. And then you aggregate away dish. You can go like that, right, with a variable elimination type of algorithm, and then you are done, more or less, right? In case of cyclic queries like this one, you don't know where exactly to start, right? You can start here, there, right? There is no, sometimes it's called ear, right? There is no ear in that graph that you can actually remove, and then you move up, and then you remove another one, and so on and so forth, okay? So it's a bit harder. So for this reason, people looked at how they could take such a hypergraph and decompose it into a tree, right? But that would be a hypertree because we still have the hyperedges, okay? And that is a result by Gottlob and others, back some decades ago, that has been applied also in AI, for CSP problems and other sorts of problems out there. And also in graphical models is used, but it's a generalization of tree decompositions, in fact, because we talk about hypertrees. If you want to understand the difference between hypertrees and trees, there is a long literature on that, right? There is a very nice survey by the same people, Gottlob, I think Leone, and I forgot the name of this guy, an Italian guy, right? And they had a very nice survey about this. And they showed that, in fact, if you use tree decompositions, you do not necessarily get all the time the lower complexity you could get with algorithms that work on hypertree decompositions. Yeah? So what is a hypertree decomposition? Effectively, we construct a pair where we have a tree and a function that maps nodes in the tree to sets of variables in the hypergraph. Okay? So for instance, in this simple query, which is a path query, this is the hypergraph. What I do, I actually take variables that, in this case, belong to the same relation symbol, and I can make a node out of them, right? So this is called also a bag, right? For some historical reasons, it's called a bag. It's a bag of nodes, right? But in fact, it's a set. But anyway, let's consider it it's called a bag. And then for BC, we construct something similar. For D, we construct CD here, we construct something the same. Okay. So what are the properties that such a decomposition should satisfy? First of all, there is a property called coverage, which essentially means that for every relation symbol or hyperedge we have in our hypergraph, right, there must be a node such that that hyperedge is included in the node. That is, we basically cover all the hyperedges we have. We don't leave out anything. The second property is called connectivity, which effectively says that if let's say two nodes have a variable in common, have a node in common, then all the intermediate nodes must also have in their bags that variable, that node. Okay? So that is the connectivity property. That is, we cannot talk about, let's say, a variable C on this side and C on the other side of the hypertree decomposition, and then in between you forget it. No, we have to remember it. We have to carry it along with us. Yeah? Sometimes this is called the running intersection property. Okay? So that is the hypertree decomposition. For our hypergraph, for instance, here, right, which is for the triangle query, it turns out that we have to put all the nodes into a single bag. And why is that? Well, simply because, well, it satisfies the coverage property, first of all, right, because all hyperedges are included in this node, right? And the second thing is it does, trivially satisfy connectivity because everything is in just one bag. Okay? But why cannot we do it differently? Imagine we would have AB, AC, BC, right? So I can actually try to write it here. If we have AB, let's say BC, and AC. So that is one possible decomposition we think of, right? But then if we do this, the connectivity property tells us that A is here, A is there, then A must be also in between. So we have to put A in there, right? But if we have A in there, then this bag already subsumes the other bags because they are already included in it. This is a valid tree decomposition for sure, hypertree decomposition, but we can have a smaller one which is just that, right? And also having the others will not improve in any way complexity of anything we can do with that hypertree decomposition. So in effect, you know, we are bound to use this. And you can immediately see that if you take any other permutation of this AB, BC, AC, you'll get with the same problem, right? So in that case, what it means is that if we have a clique, right, then the variables in that clique must actually come together, right? So you have to put them in the same bag. And what does it mean actually effectively for our algorithm, join algorithm? It means that we should somehow solve all the constraints we have on ABC at the same time, right? We cannot leave out, you know, some of them, right? Is that okay? Good, perfect. So there is an alternative way of looking at this. And I'm just giving it here because some algorithms are actually much more, they work much more conveniently with this representation. This is that of a variable order, which is more akin to the variable elimination algorithm we usually use in computer science. So in this case, a variable order for a query is again a pair where we are given a forest, a rooted forest f, and a function key which would map each variable a to a subset of its ancestor variables in that particular forest. I will just show you an example, and then I will explain the properties using this example. So for instance, if we have such a path query, right? It's a path because we go from, we have A, B, and then from B we go to C, and then from C we go to D. So we have hops like that, right? So one possible variable order would be this, right? So the nodes now are just variables. But the variables also keep with them a function key which will tell them about the dependencies they have, right, with other variables out there. For instance, in case of D, the key of D will be just C. So that is, D only depends on C. What does it mean? It means that, in general, you cannot say anything about C and D being independent, right? That is, the values that C can take would influence the values that D can take. Why is that? Because C and D appear in the same relation, right? In general, relations may exhibit any sort of correlations between C and D. You know, you can make that assumption and that you know there is a certain correlation, it may hold, but in general it might not hold. If there is certain correlation that holds, perhaps you can use that to further decompose that relation over C and D. And for that you can use something akin to tensor decomposition, for instance, right? And you can get certain parts which can then be decomposed into rank 1 terms, right? For instance. And then yes, you can actually improve the overall complexity of evaluation as well. But for our purpose here, this key information keeps us the information on the dependencies. So in particular, here in this order where we say A and then B, then C, then D only depends on C. C only depends on B because C and B come together in a relation, and B only depends on A. Okay? And A doesn't depend on anything above because it's the first guy out there, right? How can we use this information? Well, you will see later more examples that should make it clearer to you, but this conditional independence information that we store in the keys can be crucial to understand whether we can share a lot of computation. For instance, when we actually, with such a strategy, we'll first look at A values across the tables. We take those that are in common across all the tables that exhibit A. And then for each such A value, we look at the B values that come with them. But then, given the B value, the C values we get would be independent of the A values. So we could decide, for a given B value to list its C values every time that B value occurs under an A. Or we may decide that those C values to be listed only once for a B. because we know that regardless of which A the B is under, right, the C values will be the same. And that is the conditional independence, which says that given B, A and C are independent. Similarly, given C, B and D are independent, or A and D are independent. So this, again, tries to capture, but in a slightly different syntax, the very same conditional independence we've seen with the Hypertree decompositions. Now, this is a different approach, a different variable order, which says we have B at the top, and then we have a branching A and C and D. What does it mean? This actually shows even more directly the conditional independence, in the sense that if we fix a value of B, then the possible A's we can have would be independent of the C's and the D's, right? So the branches will be independent given, values for the parents, for the common parents, okay? And here again, we can further keep the information that D is independent of B given C. So that is, the key of D is only C. D only depends on C along this branch, okay? But there is something very interesting about these variable orders, and this is the following, that they somehow suggest that, if we, for instance, would like to store the result of our query, we may in fact store the A's separately from the C's and the D's. We do not have to put them together. If we put them together, we get some sort of, explosion via this Cartesian product. If we keep them separately, then we can get perhaps much more succinct representation. Okay? So that's the intuition behind these variable orders. At each variable, you do variable elimination by looking at the data. And then if you branch out, this means that whatever you do on one branch will not affect the other branches. So you can do whatever you like there. You can, in particular, store the information you have on one branch separately from the other branch. And then you can compress the representation. Good. For the triangle query, there are actually 3 possible orders here that I show. We don't have branching because of these correlations between the variables, A, B, and C. But for instance, in the first case, you see we have A, B, and C, this order we decide. So what can we say? Well, if we actually iterate over the A's, for a given A, we can then have the B's, right? And for each A and B, we have the C's. Now the C is not independent of A given B, because A and C also occur together in a relation. So they may be correlated in some ways we don't know by just looking at the query. Okay? So this is again hints to one important observation, or let's say, strong assumption used in databases, namely that it is fine to look at the query, and you can do whatever you like with it, to optimize it, to get the best variable order you might want, or the best Hypertree decomposition. And that may take, in fact, exponential time to do that, but only in the size of the query, which is very small. And in all cases, is mostly considered actually to be of constant size. Whereas the data may be very large, right? So when we actually reason about complexity here, we normally reason about data complexity, so-called data complexity. So the complexity where the input, n, represents the number of records we have in the database. And we express it as a function of n, that complexity. Whereas for the size of the query may be in fact something like, maybe in some cases exponential, but that is just for a small quantity. Right? Now obviously if your query is very large, like 100 joins, then that will hurt as well, right? Unless you have other ways to deal with it. You cannot just do exhaustive search through all possible variable orders or Hypertree decompositions in that case. And that is a research topic on its own, right? And similarly for the other permutations of A, B, and C, you will see that in fact C, if you put it at the bottom, will depend on both A and B because it appears in relations with both A and B, right? So there is no independence we can actually harness there. It's a click, and that's it. Okay, good. So there is in fact a very easy translation between the two. I will first show you a translation between Hypertree decompositions to variable orders. So this one is from variable orders to Hypertree decompositions, and after that I will show you the other way. So if you have such a variable order, what you do if you want to construct a Hypertree decomposition, you look at every single variable, let's say every single node, for instance C, you look at its keys, right? And then you union the keys with the node itself, and that gives you a bag, right? and then for AB you get a bag, and then you get a bag here. By way of constructing these variable orders, you'll always get a connectivity and the coverage property. In this particular case, you also see that two of the bags are subsumed by another one, so you can just discard them, and then you get one node in the Hypertree decomposition. Now, for the path query, we then can construct C and D, right? It's the key of D union C, union D, and then key of C union C, and so on and so forth. And then again, here we observe that A is subsumed by A and B, so we can drop A, for instance, right? So what about the other directions? For instance, if we actually start with the triangle query, and we know that the Hypertree decomposition for it was just a single bag, right, a single node with all the variables in it, then one thing is we take one of the variables, let's say we take A, and then so that will become the root. Its key will be empty because there is nothing above it. And after that, and we remove it from our bag. And then we pick another one. Let's say we pick B. And then we know that B will depend on A. They were in the same bag, right? So the key will be that one. And then we create the other one, the node C. And the key of C will depend on the other guys which were in the same bag. Right? So that's the way we can go back and forth between these two. So this is a bit more refined in the sense that it already fixes an order of the variables, whereas the Hypertree decomposition does not fix that. And sometimes it can make a difference because you may have more A's than B's in a table, let's say. Good. So for the path query, well, we first take, let's say, the variable A. We decide on the variable A, so we make a node A in the variable order, and then we look at B. We put B and A were in the same bag, so we can actually put the key of B to be A. And now we basically erased A, B, and from the first bag and B from the second bag because we used it already, right? So we already eliminated the variable, and now we are left with C and D. So what we do, we put C, right? Because that was remaining from the second bag, and now the key of C would be just B, because this is the only other variable which was on the same bag. And then at the end we put D, and we are done. Okay? So these are the kind of tools we will use now. The Hypertree decompositions and the variable orders. Let us now reason about size bounds for listing representation of the join results, right? So it is very important to understand for various problems, what would be the size of what you generate, what you create with your query. Why? Because depending on that, you may decide to use a certain strategy or another strategy to compute the query, right? If you know that the size will be anyway small, perhaps you can do it in memory, and then you may employ different techniques to do that. If you expect that the size is very large, then you may want to employ, I don't know, other operators that actually will write to disk, will do other kind of trade-offs in there, right? So that's the kind of holy grail of database management systems, the relational ones, is to understand to what extent the sizes of the results and of the intermediate results, right, are large or small. And for instance, in database systems out there, if you use, for instance, Postgres or anything, if you write a query and then you can put an explain in front, or sometimes there are other keywords, it will show you what would be the strategy used to evaluate that query. And next to every single evaluation strategy, let's say, operator, it will tell you also what they think about the cardinality of the result of that operator. Yeah. So depending on that, they justify their use for the different algorithms, because a join may be implemented in very many ways in databases, using a hash approach, hash-based approach, or a sorting, or you can distribute it, you can over several machines, or you can use multi-core and so on and so forth, right? And that depends a lot on the kind of optimization, let's say, strategies you use. Okay, so because of that, it's very important to understand something about the bounds on the sizes of the join results. In particular, how many tuples we have in the result, how many records we have in the result. And getting a tight size bound has been elusive for a very long time, but we will see today that in fact you can get tight size bounds, which then later on you can use them perhaps to derive an optimal algorithm for doing the join. So how can we bound the size of the join result? So imagine we have this path query, okay? R1 join with R2, join with R3. the moment we make the simplifying assumption that all relations have the same size n, right, so that we don't get messed up with this. And later on we will see what happens if we get different sizes of the results. So if we look at the query long enough, we realize that if we actually join R1 and R3, in fact there is nothing to join between them, it's just a product between them, that must be larger, must include the size of the result, right? Because R2 has additional information on the B's and the C's. Would only tell you that certain B's with certain C's will be combined. Worst case scenario, R2 says that all B's will be combined with all C's, right? It's a Cartesian product of the two. But in most cases, it is not the case. Okay? So in that case, we say, okay, the result is included in the result of just taking the product of R1 and R3. So this means that it can be at most quadratic. If the sizes would be just n for every relation, right, then it can be at most quadratic than the size of the result. So in other words, the way we could explain ourselves this is that the variables we have in the query A, B, C, D would be covered by relations R1 and R3. So all these variables can only draw values from these relations, right? And that gives us an upper bound. A, B, C, D, would cover both, will be covered by R1 and R3. However, we can also construct databases for which the result size is at least n squared, right? How can we do that? Well, let R1 be just, n distinct values paired with a single value in the second column, right? It still has size n, right? The second relation is paired with the, has for B just 1, but has n distinct values for C. And the third relation has n distinct values for C and 1 value for D. Now, for this particular setting, right, if you actually do the join, it effectively boils down to, roughly to a product between R1 and R2 because, we have a single value, so they join only on that value. So R1 join R2 will give us n squared. And R3 will not filter anything from this because it still has the same domain as for C as it is domain of C in R2, right? We'll just extend every tuple with another column that has only 1, 1, 1, 1, 1. Okay? So in other words, in this particular case, we can say, hey, we actually found an asymptotically tie-size bound, which is, a worst-case analysis. It's not, an instance-based analysis, which tells us that for all databases, this is n squared. No, in some cases, it may be lower than n squared. But in worst case, it is n squared. Yeah? So in that case, we are happy. We say, yes, yes, okay. So we got actually this. So the size of the result is theta of n squared for some inputs. Yeah? So what about our triangle query now? So for our triangle query, we also can see that if we join any of the two relations, then that result, which will be an intermediate result, subsumes the final result. Why? Because if we join R1 and R3, right, we get all pairs A, B, C, and R2 may only filter out some pairs A, C, in fact, right? It cannot add to this, right? So R2 in that case serves as a filter, as we discussed also before. So in that case, we can say that an upper bound would be n squared. But, and we can also, in other words, we can say that, yes, all variables A, B, and C are covered by these two hyperedges, by these two relations, R1 and R3. So they can draw values from these two relations. And then we are done with it. Okay? But if we want to get a lower bound, then that's actually harder. And, thinking about it, you could see that perhaps you can get a result size which is at least n, so linear. Yeah? Because you can say one of the relations is n distinct values times a single value, then R2 may be n distinct values times one value, and then R3 must contain at least 1 and 1, so we actually join on this and then on the other, right? But then if you join them up together, you get, for that kind of, for that class of databases, you can only get a lower bound which is linear. So the trouble is, well, we get a gap between the upper bound and the lower bound. Can we actually close that gap, is the question. Yeah? So the answer is yes. but perhaps not immediately clear. It has been only clear, about 10 years ago, I would say, right? In a paper in Soda. So, but in order to reason, systematically about these bounds, let us first see how we can phrase these questions as edge covers and independent sets in the hypergraph. So, for the size upper bound, what we did was we said the following. If we look at all the nodes or the variables in the query, and we can cover them by k hyperedges or relations, then we know that the size is at most n to the k, right? Because we have these variables there, they draw values from these relations, right? So if we take these relations and we know they cover all the variables, then that's it. We are safe. This is an upper bound. Then we look at that particular number of edges, and we say that in worst case we take a product of all the relations, representing these k hyperedges, and then we get this size, which is a very, very generous upper bound. Okay? So for the lower bound, what we actually want, in fact, is to look at the variables in our hypergraph and look at the independent set of them, right? We try to take independent variables, because this means that one will not influence the values for the other, so we can pump in the domain of each of them, n distinct values. And then the lower bound will be essentially the n to the power of this maximum independent set. Okay, is that clear? Because the variables will be independent, right? So one will not influence the other, the values that the other can take. So we can pump n distinct values in each of them, and then we get a blow up. So that's the thing. So on one hand, if we want upper bounds, we look at edge covers. If we want lower bounds, we look at independent sets. And it is known that the size of the maximum independent set is less than or equal to the minimum edge cover. Okay? So for the upper bound, obviously, we try to minimize the edge cover, the number of relations covering it. In the case of the independent set, because it's the lower bound, we want to maximize. So we take the maximum independent set. Right? So they do not necessarily meet. Right? And that is the observation. Right? You can actually, for each of them, have an integer program that actually uses as input the hyperedges and the nodes in the graph. And then you can compute a maximum independent set and a minimum edge cover. But they don't meet. So the issue is that they would meet if we relax these programs, the integer programs, to compute the true values, to a linear program. So instead of taking actually an integer cover value or an integer size of an independent set, we take a fractional variant. Okay? And that is the catch, right? What does it mean, actually, in layman terms? It means that we may use now to cover a particular variable, we may use a fraction of a relation and a fraction of another relation containing it. Instead of just deciding, well, for that variable I use exclusively one hyperedge or the other hyperedge, one relation or the other relation. I can, for instance, use the square root of a relation from, of one relation to cover this, and square root from another relation to cover the same thing. Right? So now I have fractional edge covers and fractional independent sets. I don't deal anymore with the integer versions. Okay? And that's the whole idea. They will then meet, because these programs for the fractional independent set from the fractional edge cover, they are dual. And by the duality of linear programming, you get the same solution. Okay? So that is the thing. So then, in that case, you have a parameter which is the fractional edge cover, which is called the fractional edge cover number, and this is depicted as rho star, because rho is the integer edge cover number, right? The fractional one now is called rho star, okay? And that rho star, we can compute it from the hypergraph. You take the hypergraph, I will see in a second, you can construct a linear program out of it, and that will give you the fractional edge cover number. And that can tell you, okay, this is the size, in worst case. Yeah? And that's the very, very important observation here. And that applies for both upper bounds and lower bounds. Okay? So if all relations have the same size n, then we know that for any join query and a database of size n, the query result will just have this size, O of n to rho star of q. Rho star of the query q, which is the same thing as the rho star, or fractional edge cover number of our hypergraph of the query. Okay? So that is the very important observation. So what is the actual linear program to compute this? This is the following. So imagine you have a general join query that you join relations R1 to Rn. Each R1 to Rn would have a set of variables, A1 to An. Okay? So these are sets. And in the head of the query Q, we have a union of all these variable sets. So we take all of them. So we don't project away anything. Okay? So this is the program. So what do? We say for every edge, for every, essentially, for every node A, right, that is for every variable A in our query, we look at all the hyperedges that cover it, and we associate with every hyperedge, or with every relation, we associate a weight, which is a fractional number. Okay? And the sum of the weights for every variable, the sum of the weights of the edges intersecting on that variable must be at least 1. That is, that variable must be covered fully. Could be covered a bit more than necessary, okay? But, at least should be covered with a weight of 1. In the previous approach, where we did integer programming, then these weights could be only 0, 1. So we decide we use the hyperedge or we don't use the hyperedge. But now we can say, let me use the hyperedge only partially for this and partially for another hyperedge I can use for the same variable. Okay? And that's the thing. Then obviously these weights must be greater than 0. It doesn't make sense to have them greater than 1 because you just need to cover every variable by a weight which is 1. Right? So if you want to cover it by 2, then obviously we can do that, but that will not give you an optimal solution. Because effectively what you want at the end is to minimize the sum of these weights. And the sum of these weights will tell us, what would be the complexity. What is this rho star? What is this fractional edge cover number? Okay? So I will show you examples for this. Take this query. So we have R, S, T, and U. We join them. We join R and S on A, and so on and so forth, as it is depicted in there, right? So the hyperedges would look like this. R covers ABC, S covers ABD, T covers AE, and U covers EF. Okay? So now, if we want to cover all the nodes, I think it's enough to use R, S, and U. So those particular hyperedges. Because if we use R, we already cover ABC. If we use S, we cover also D. If we use U, we cover F and E. A has been already covered by both R and S. So now the question is, which weights should we give to these hyperedges? Now, obviously, to R, we could give a weight, let's say, of 1/2, so 0.5. Would that be enough? Not quite, because C has to be covered with a weight of at least 1, and R is the only edge, hyperedge, that actually could cover it. So we must give a weight of 1, at least 1, to R. Greater than 1, as I said, it doesn't make sense. So the weight of R will be 1. The same reasoning we can apply for D. So we have to give a weight of 1 also to the hyperedge S. And similarly for U, because F is alone, is only covered by U. Now, we cannot get better than this, right? While also satisfying our constraints in the linear program, so that every variable is covered by a weight of at least 1. So therefore, we conclude that the rho star, the fractional edge cover number in this case, is 3. It is, well, it is at least at most 3, but by doing the reasoning I mentioned before, it must be 3. It cannot be lower than 3. So then we conclude that the size is at most cubic, and for some inputs, it may be actually, it will also meet a lower bound. We can get a cubic lower bound there. Okay? Good. So let us actually look at our triangle query, our culprit, that actually we noticed for it, there was a gap between the lower and the upper bound. Yeah? So what can we do? So that would be the actual linear programs specialized to our query. So we effectively say this. Variable A is covered by R1 and R2. So the weight of R1 plus the weight of R2 must be greater than or equal to 1. Variable B is covered by R1 and R3. So the sum of their weights must be greater than 1. And for C, R2 and R3. And all of them, all weights must be positive. Yeah? Now, if you think harder about it, one way to basically bound this is to say, well, if I give R1, XR1, so that weight I give 1, and the weight to R2 is also 1, then indeed all these inequalities are satisfied. And that was exactly our reasoning from before, that we can get a quadratic upper bound. Yeah? But we can get better. So if you think about this, yeah, you may be able to allocate a weight to each relation which is less than 1. And that is what we can do. We can allocate to, we can set the weights to be 1 over 2 for each of them. And if that's the case, then every single node, every single variable is covered by a weight of 1. Okay? So it's a weight of 1, a weight of 1, a weight of 1. Everything has a weight of 1, and then our fractional edge cover number would be 3 over 2. Yeah? And then the lower bound, for instance, could be reached when all the three relations would be just the Cartesian products of square root of n values on one side and square root of n values on the other side, and it will be reached. Now, arguably, this is obviously a very, very contrived lower bound. It is true. If you want to talk about asymptotic complexity, these things make sense. In practice, however, you might think that you can get better than this, right? In particular, for this particular setting, where the relations are just products, you may actually do better using other techniques, right? So it is true, right? And therefore, there are more recently works trying to go beyond this fractional edge cover number. Good. So this is another example. This is actually a loop 4 query, a 4-cycle query. So we actually go from A1, A2, and then we go A3 below, and then A4, and then A1 up. So it's a cycle. So in this particular case, the linear program would look like this, right? For every variable, we have actually 2 edges covering it, and so this is the linear program with inequalities. So what could we do? Well, one possible solution is to set, for instance, for R and T, the weight 1, and then all relations, all variables are covered, and then the fractional edge cover number would be 2. Which means that we can actually have quadratic size of the result. And we can, as we will see later, we can also compute it in quadratic time. But there is something quite interesting here, namely that, and I will not dig into it, there may be a more adaptive approach which actually would not consider a single variable order or respectively a single Hypertree decomposition to evaluate the whole query, but for different parts of the query may use different strategies, in which case we can actually lower the complexity from n squared to n to 1.5, actually. And that new notion is called the submodular width, which is something that popped up more recently, but I will not cover it here. But so there is still some work that popped up after I made these slides. We can actually refine all this analysis we did before under cardinality constraints. And one way to do this is to think that relations in practice may have different sizes. We so far made the assumption that all relations have the same size n. So we may also have additional cardinality constraints of the form, we know I know I have only a certain number of distinct values in that column. So we would like to use that to better guide our search. What can we do for that? Well, if we have a certain projection of a relation with a certain size, we can just add this to the join query as another relation. So we join with it. And this means that our hypergraph will get extended with another hyperedge, and which means also that we may now be in the position to allocate a new weight for that particular hyperedge. And but nevertheless, even if we just don't have additional projections, but we have just the weights of the original relations, we can actually adapt the linear program to take relation sizes into account in the following simple way. First of all, instead of computing the fractional edge cover, we can compute directly the size, so which is basically the n to the power of this fractional edge cover, right? Which is exactly what we did so far. And then the second thing is, obviously from here, we can actually express this as n to xr1 times n to xr2 and so on and so forth, which gives us a product of n to these weights. And then we can actually just, instead of actually using the same n, right, we can change it to use ni, which will be the size of each relation. So now we have to minimize for a different goal, for a different objective, which is taking also the relation sizes into account. Which may mean that if we have, for instance, n1 very, very small, right, we may decide to give to the weight of that relation, to increase the weight of that relation to cover more variables, because we have a tighter constraint on that particular variable. Okay, and that's about it. Okay, what I presented so far is something that could apply to relational database management systems out there. Nevertheless, they do not necessarily use the kind of technology we discussed here. And for that, they may be, in fact, suboptimal. They may construct those quadratic size results, intermediate results, in case they would do a triangle query. Okay? But now I will show you a bit more work on how to lower the bound on the size of a relation, representing the query result. And by this I mean a factorized representation. So we try to factorize the representation of such a join result. So let us look back at our original join example. Right? We have the three tables, ordered this and items. We joined them, and then we looked in the result, and we've seen so many repeating values. Right? Alice appears, for instance, here 6 times. Right? Monday 3 times, Friday 3 times. Burger appears again 6 times. But then we also see that it's not only about single values appearing over and over again. We also have blocks of values appearing, right? Such as patty, onion, bun occur over and over again, because they are the constituent parts of, in this case, a burger. Yeah? So we'd like to somehow represent the data differently so as to avoid such a redundant representation. So how can we do that? Well, the first step we have to do is to depict this in a more relational framework, which would make us comfortable to factorize effectively. So I look here now at the bottom of the slide at records that are at the top, but relationally, in relational algebra. So what I say is that every value becomes a tiny relation with just one value and one column, like Alice, like Monday, Burger, Patty, and 6. And a record up there, below here, becomes a product of such small records, okay? Such small relations, sorry. If we have several records up there, this means we have a union of such products, Cartesian products of small relations, which we can call singletons. Yeah? And now we can simply apply laws of relational algebra. Yeah? We have a union and Cartesian product, in a sense, could be, you can think of them as plus and times in a sum product semi-ring, right? And then you can start applying, the law of this distributivity. So you can actually factor out terms that are common to several such products. And here is, for instance, one particular representation. What does this say? Well, this says the following, that I use a particular variable order, dish, day, customer, dish, item, price, okay? That is given dish, day, and customer will be independent of item and price, okay? So I first iterate over the dishes, so I have burger and hot dog. So I have a union of 2 possible dishes. These are the only possible dishes I have in my result, burger and hot dog. And then given a dish, in our case burger, then I can store the data about day and customer separately from the data about items and price. Okay? In particular, I have 2 possible days for burger, Monday and Friday, and for each of them I have Alice. So I could further factorize this, for instance, right, to represent Alice only once. On the other hand, for hot dog, I only have Friday, and both Joe and Steve ordered on Friday that hot dog, well, a hot dog, sorry, and then the bun, onion, and sausage, they come with their prices as listed in that third table, which is the item table. Yeah? So that is a factorized representation of the join result. Is this actually smaller than the listing representation? Yes, for several reasons. One reason is that obviously burger is only represented once instead of representing it very many times. But most importantly, the succinctness comes from the fact that this Cartesian product here is symbolic. It's not explicitly materialized. So we don't take all days and customers and multiply them with items and price. But rather we keep these Cartesian products more symbolically. We just say there is a product between this and that. It's also easier to look at this and comprehend instead of actually having all the possible combinations, right? And then having to discover for yourself there is structure in those combinations. The structure is made explicit here. And that can be obtained for this particular variable order. If you give me a different variable order, I may end up with a different factorized representation of the result. Yeah? And there are then algebraically equivalent factorized representations. That is, they represent the same relation, but they may actually have different nestings. Right? So they may also have different sizes because of that. And what we do here, we simply use the distributivity of product over union and the commutativity of product in union, which are just laws in semirings in this particular case, right? The union product semiring. And given a variable order, its factorized representation, or in other terms called also the grounding, is unique up to commutativity. Yeah? So we can compute, instead of computing the flat relation, the listing representation, and then compact it like that, we can in fact, given a query in the input database, we can compute directly this factorized representation. And that is also something very, very useful, because we can avoid the blow up given by these large relations. Okay? Now we can have a different factorization. For instance, here, I, as you can see, share the prices for bun across several dishes. Why would I do this? And why am I allowed to do this? Well, for the simple reason that given the item, the price and the dish are independent of each other. So the price for an item is the same regardless whether it appears under hot dog or under burger in our example. And that's the conditional independence we already exploited and stated in our variable order, right? So here are the keys. The key for the price is item, the key for the item is dish, and so on and so forth, okay? Now, this sharing here, this caching, is actually very limited. You just cache a value, of a price. But imagine more complex queries where what you cache here can be an entire subtree, can be very, very large. And in fact, by caching, you can reduce further the complexity of this. Yeah? And by this, I mean, you can reduce it exponentially. Yeah? Good. So, same data, different factorization. Now I take another variable order, which is just a path. So I basically first enumerate all the days, and for each day I enumerate all the customers. For each customer I enumerate all the dishes, and then for each dish all the items, and then all the prices, right? So it's more like a trie representation of the data, following this particular order. But hey, we forgot something. We forgot that we have some conditional independence in here, namely that given item, price, and dish are independent, given dish, item, and customer are independent, and so on and so forth. So let's plug them in. If we plug them in, suddenly we can share a lot. Yeah? In particular, the burgers will have obviously the same items inside. Yeah? So we can then represent the information for the burger only once. Right? This information with the items. And the same for prices. We also notice that bun and onion are items that are used in both burgers and hot dogs, but the prices are the same. So you can further share this. So this sharing can be really, really deep, actually. Right? And can maintain a size of this essentially linear in the size of the input database. Whereas if you would actually do the join, you'll get quadratic. Right? But that remains linear. So this brings us to the following point. Okay, so which factorization should we choose? Should we choose one over the other and why? Well, obviously, one measure to compare them is the size. And by this I mean the number of values we have in the representation, let's say, right? That is, if we consider this particular example with F1 and F2, F1 is a factorized representation that looks at pairing n distinct values with m distinct values. But it just says there is a product between this, but I don't materialize it. The second, equivalent representation, F2, really pairs explicitly each value from one side with each value from the other side, right? So we take one with 1, one with 2, one with m. Union, n with 1, n with 2, n with m. So now the first one has a size n plus m. The second one has n times m. So we should favor the first over the second. Yeah? And in this sense, I mean that we should perhaps look for factorizations that actually have smaller sizes. Ideally, the best possible size. Yeah? So how much space does factorization save over the listing representation? And here is, a string of results. First of all, the result from 2008 by Atserias, Grohe, and Marx, they said this. Well, if you give me a join query, such as the ones we've seen before, and a database of size n, then the join result would admit such a listing representation, record by record, of this size, n to the power of the fractional edge cover number of the query. This is exactly what we discussed before the break. Yeah? But now, if you actually want a factorization without caching, that is, we do not want to have DAGs, but rather just trees, right? We don't want to explicitly exploit the fact that some blocks of data may be repeating, so you can actually just have them once. Then we get, instead of the row star or fractional edge cover number, we get another parameter, which I will explain in a second, yeah, S, which is less. And if we go further and we use caching, then we get to another parameter, which is called the fractional hypertree width, yeah? Which perhaps you heard of the tree width, right? The hypertree width is the version of tree width where we consider hypergraphs instead of graphs. And now the fractional is the one where when we compute the width, we take the fractional, the linear program instead of taking the integer program to compute. And there may be arbitrary gaps between the linear and the integer program solution. Yeah? So in particular, if we order them on a line, right, where one means, well, we take linear time to do things, right? And on the other extreme, we get the number of relation symbols. That is, we need, let's say, if we have 5 relation symbols in the query, this means that it takes something like n to the power of 5 to do the processing. Then the other parameters are somewhere in between. The most compact one, representation, is the one with caching, factorization with caching, and that gives us the fractional hypertree width, which is very close to 1. It turns out that for all acyclic queries, such as the ones I mentioned before, like the paths, right, the fractional hypertree width is exactly 1. So that is, you can actually do the joins in linear time. Well, modulo, in fact, some logarithmic factor, because you need to sort the data initially. Or perhaps if you use hashing, then you may skip that logarithmic factor. But then the next step is, if we don't use caching, so we don't use this, DAGs, the DAG representations, directed acyclic graph representations, but then the gap is up to the logarithm in the number of relation symbols in the query. And you have to think that these parameters are actually the exponents of our complexity. So we basically, reduce massively our runtime if we go from no caching to caching in our factorization. And then the last parameter in the line here is the fractional edge cover number. And the gap between factorization, even without caching, and this parameter can be up to the number of relation symbols in the query, right? A simple example could be you take a product, Cartesian product of n relations, then the row star is exactly n, right? The number of relations you take in the product, whereas S will be, in that case, 1. Okay? So the lesson we can draw from here is that eagerly materializing Cartesian products is not necessarily a good idea. Okay? It is detrimental for space, because we have to store much more. And we can be a bit smarter about the way we store. And it's also about the time, because we may need less time to construct such representations, in fact. Now, what are some direct implications of this? Imagine that we use a factorized representation for our join result. Then suddenly, things that couldn't fit in memory may fit in memory. Yeah? Much, much more data you can fit in memory. And in memory, you can do then zillions of things much faster, right? Than actually if you have to page in data from disk all the time, and then page out, and then page in again because you don't have enough buffer pool for everything and so on, right? So you effectively can reduce dramatically your I/O cost, of the computation. An additional thing is that also the CPU cost can be reduced dramatically because of this gap, right? To produce this result may be very large and a lot of redundancy in it, whereas you can produce a much smaller result. The tricky thing is now, what can you do with these things? What can you do with these compact representations? Can you do anything with them? Well, for one, I can tell you, you can do one very important fundamental thing. You can enumerate the tuples in the result of the query with constant delay. What does it mean? It means that if I compute such a factorized representation of the result, and I have a user who says, list for me the tuples in the result, then the time it takes from showing one tuple and showing the next, also in a particular perhaps order of the tuples, right, may take only constant time in the size of the data. It may take linear time in the number of variables you have, right? The size of the tuple is linear, but in the size of the database, it's just constant. It doesn't depend on the size of the database, right? And that is crucial for several reasons. One important reason is that if you have such constant delay enumeration of the tuples, you can do aggregates efficiently, right? That is, we will see in a second, you can actually compute a count. Let's say, count me the number of tuples in the result. Do a sum over a particular column. Group by, that is, you have a free variable as well. Things like this can be done in one pass over the representation. And why is that? Because this representation tries to somehow go as succinct as possible while at the same time still maintaining some operations tractable, right? By using product and union, right? Product essentially says if you want to search for anything, if you are at a product as you come top down, for sure you have to look in all branches. Is this and that and that and that. This means product. Union means alternative. You are at a union node, you say, well, it can be there or there or there or there, but these unions are deterministic. You do not represent the same information under different children of the same union, right? So because of this sort of, design ideas, right, we can actually use factorization for loads of things that come on top. Good. So, and the interesting thing is that these sizes are asymptotically tight, these sizes. This means that these are the best possible size bounds for factorized representations over variable orders and for listing representation. That is, in worst case, you cannot get better than this. So these are the parameters actually governing the tight size bounds, okay? But they are not database optimal. If you know something specific about a database, like in a relation you have a functional dependency, or you can break down the relation into two pieces that are just products of smaller pieces, right? Then you may do better than this, obviously, right? But if you have that, you can perhaps, already change the data so that you make explicit this decomposition of the data, and then you can reflect it in the query, and then you get again the same analysis, and you get a lower fractional hypertree width, or a lower fractional edge cover number. Okay? Good. So let me give you some examples, some intuition for these widths of for factorizations, right? So first of all, I will look at the case without caching. So remember, we had this particular this particular variable order before, right? That is, we said, well, given A, B, C, D would be independent of E and F, right? So that it says, or given A and B, C and D are independent of each other. Okay? So what is the actual intuition for using the factorization to lower the complexity of the size? Well, again, the information you store for a C, that is the possible C values you have under a particular AB, would be independent of the information you have on the F, right? So if you want to look at the fractional edge cover number, to look at for the size, you don't look for the whole size of the result, but you look only for this query, right, that looks at A, B, and C only, the variables, right? Because the number of C values is only dictated by the A and the B's, the possible values for A and B's. It's not dictated by f. So in other words, if you want to get this parameter s, which governs, the sizes of the factorizations, right, without caching, the only thing you have to do is to restrict your query to a subquery that only looks at every root to leaf path. And for those queries, you then take the fractional edge cover number. And that's it. And that gives you take the maximum over this, right? Because some branches may be more costly than other branches. And that gives you the parameter s. And that gives you the complexity you need, for storing and for computing such things, such factorizations. And that's about it. Let me actually go a bit further. What about the fractional hypertree width? Now we use also the key information. So in addition to using the branches, we use the key information because along a path we may still have independence, conditional independence, right? So now when we actually want to understand what is the size of the representation, we look at what would be the size of the representation for f. And for that we say how many possible f values we have under its ancestors on which it depends, right? F only depends on E, it doesn't depend on A, because this is what this information tells me in the variable order. So because F only depends on E, to understand how many possible F values I have, I just look at the query defined by E and F. In other words, if the same E value occurs under different A values, this E value will appear with the same union of Fs, with the same values F, will not appear with different ones, because F does not depend on A. Yeah? If F would depend on A, then obviously we'll have to understand how many F values we have under each pair A, and E, right? But in our particular case here, we know that F only depends on E, so we look at, what would be the maximum number of possible F values we have under an E. And that would be linear because E and F appear in the same relation, U. What about A and E? Again, for E, we know there may be at most linearly many because, E and A both are part of a relation T. What about C? Well, A, B, C appear in the same relation, so the maximum number of C values you can have would be, given by the size of the relation R. You cannot have more. What about D? Well, you have A, B, D a relation, okay? So then in this case, you can actually get again linearly many Ds. How many Bs? At most linearly many, because B draws values from a relation R or from a relation S, and they are all of the same size N. Okay, right? So in this particular case, it turns out that the representation will just have linear size by using the caching. Before, here, the representation, how many Cs? The same reasoning, linearly many. How many Ds? Linearly many. How many Bs? How many As? Linearly many. But how many Fs? Without knowing that given E, A, and F are independent, right, we have to think that F has to depend on all possible combinations of E and A and E. Right? There are linearly many, and for each E, there may be linearly many Fs. So it will become quadratic in that case. Right? So in that case, basically, we look at the fractional edge cover number of the query defined by that path, A, E, and F. Whereas in this case, we only look for each node, right, at the query defined by its key and the node itself. And that's the gap. So here would be quadratic. In our case, it would be here for fractional hypertree, it would be linear. And if you would actually think about the listing representation, the row star, we discussed about it, right? You can pump as many n values in C, n values in D, and n values in F. The fractional edge cover number will be 3. So with this, basically what we get is this picture. For this particular query, if you want the listing representation, could be of cubic size. If you want the factorization without caching, would be of quadratic size. And if we want the factorization with caching, where we additionally have caches along the branches, we get then linear size. Right? So much, much more compact representations. Good. So there is indeed an alternative characterization of fractional hypertree width, which was the original one done for hypertree decompositions. But I wouldn't insist on it now, but it is on the slides. If you have questions, please ask. Or if you have now questions, please ask me as well. but I just wanted to put it for completion. But essentially, it boils down to the same thing because of the equivalence between Hypertree decompositions and variable orders. Now, I want to tell you one extra thing about factorizations. You know, factorization, I actually spent quite some time talking with people in the Bay Area about this idea. I said, okay, look, there is something interesting. You know, it will speed up your queries. And they said, yeah, Dan, but you know, everything is fantastic, but how can I possibly use this? My storage is relational because we designed it like that. You now ask me to change my whole thing just because you have now a different representation, a cool representation, right? So we tackle these problems in two distinct ways. One way, as you will see a bit later in part 2, is as follows. Instead of actually explicitly materializing the factorized representation, we look at this factorized representation as the trace of our computation. We never materialize it. But when we compute aggregates over joins, this factorized representation is the way we do the computation. You know, at any one time, you know, a path in this factorized representation represent what we do, right? And then we backtrack, and then we take another path, and so on and so forth. So we never materialize it. A second thing, which is what I'm going to talk now about, is the following. We very recently realized that we can get all the benefits of factorized representation, but storing it relationally. So this sounds magic. It sounds like, you know, you are telling me that, you know, you don't need to actually factor out things. You can just, you know, take a few records, and that would give you the same size as a factorization, while at the same time being relational. The answer is yes. Yeah, and that's what we did very recently to appear in 2 months. It's called covers of query results. And the idea is simple, and I will show you with an example. The idea is that if you look at the query result, you know, long enough, and we had to do it, you know, because weather was bad, so there is nothing to do outside. We looked at it, and then we realized if we carefully choose some of the records in the result, a minimal number of them, those records may be enough to characterize the whole result. So you wouldn't need to store all the other records, because those minimal ones may actually, in fact, you know, help you derive all other ones. Yeah. So that's the thing. So that's the kind of, you know, brilliant aspect of it, that you can, in fact, take a very small subset of the result, and that may have size which is governed by the fractional hypertree width, and that may be exponentially smaller than the size of the full result. And being relational, now you can store it, you can play with it, you can actually ship it over the network, right? One major motivation for that was, for instance, in discussions with the guys at Google F1, they actually said, you know, for our distributed system, the major bottleneck is communication cost in a distributed system, right? So we have a query that is evaluated in a distributed setting, and this means in each round we do a join, and after that we have to shuffle the data, you know, to the nodes for the next round, and then again shuffles. And these are intermediate results of the query, so join results. If you are telling me that you can actually allow me to shuffle much less, so I can actually minimize the communication cost, then that's great. It's great for latency, obviously. It's great overall for energy consumption and so on and so forth. And that was one of the reasons we looked into that, right? So we maintained the very nice complexity, but while at the same time we do it very, very simply. So let me actually show you this. So we start with the relation, the input database, and now this is the representation of the result. And we also start with the, let's say, Hypertree decomposition of the join query, right? Where essentially every bag, every node is represented by one of our input relations. What can we do now? Well, let me first put the information from each table up there, right? So at least Monday burger and at least Friday burger would be tuples from the relation customers. Then for this particular excerpt of the result, then burger patty, burger onion, burger bun would be the other distinct values for the second table, right? So if you take from this table and you project on dish and item, right, you get this information. If you project on customer, day, and dish, you get the other result, right? And now for the last, we get the patty and the item and price. So what are these tuples here in the result? What are these records? Well, they are these hyperedges in this join hypergraph. So if you consider that every tuple in the input is represented by, like here, by a node, right? Then a tuple in the result is the combination of such tuples from the input. So it's a hyperedge, if you like. But now of the data, not of the query. Okay? So that is a hyperedge. Now, the second tuple represents the second hyperedge. Another hyperedge, yet another one, yet another one, yet another. Look, so many of them, right? But if you look at them, one thing we learned from the other work we just learned about, right, is that we can actually, every time we deal with hypergraphs, we can take minimal edge covers. And minimal edge covers would tell us everything we need to know there. Yeah? Not in general for general hypergraphs, but for those hypergraphs that are generated as results of queries. Because essentially, intuitively, the idea is this. Imagine I have two tables, R and S, and I take a product of them. A product, if I look at it as a graph, it is a bipartite complete graph. It's bipartite because, you know, I have two sets of nodes. One set of nodes represents one table. One set of nodes represents the other table. It is complete because the product tells me I take all possible edges. Now, for this information, if I have it, right, I would say, traditionally, when we look at that, we say the information is in the edges. We store all the edges. But in fact, the information is in the nodes. Here, the edges tell us everything is paired with everything. So if we just take the nodes and we just have a single bit saying everything paired with everything, that describes completely our complete bipartite graph. Because that bit says yes, everything with everything. Okay? So that's the way you can think of it. So then, if you take a minimal edge cover of this bipartite complete graph, so basically this means that every node is covered by at least an edge. All other missing edges, you can actually derive them from the edges you take already. It must be minimal in the sense that if it's not minimal, this means you actually keep some edges which you don't need, right? Okay? And it must be an edge cover because you want to cover all the nodes. That is all the tuples that are relevant. Okay? So that's the whole thing. So here, now, we just take this, and that would be a minimal edge cover. It's a hyperedge cover, minimal hyperedge cover. So why is it? Well, first of all, every node, every tuple from the input, which is relevant for the output, is covered. Okay? And it is minimal in the sense that if I take away a hyperedge, then I don't cover all the nodes that are relevant. Right? And that's it. Right? If I put this back, this is all the information I need. And that captures everything I need. So instead of this very large result, which is not even completely written here, I can just keep that. Well, for this part is just that, right? And I'm done, right? This is what I will ship around the network. This is what I can store. Every time I need more, I can iterate over all the missing tuples again with constant delay. So there is an algorithm that, given this, can produce the remaining tuples, with constant delay. As if I would list them, I mean, from the user perspective, the user gets a screen with all the records anyway, right? And the way they are produced is also with constant delay, one after the other, reading it from the file. Similarly here, okay? So that's the kind of, additional thing I wanted to mention, that now there may be actually potential for this to be used by other database management systems which are purely relational, and they would not like to actually come up with another storage layer which is, for this graph data. Good. Compression by factorization in practice, just a very, very brief note. We did an experiment. We took this, data set, orders, addition items for the purpose of this, and we said, what if we have a listing representation in comma-separated value format? Then we want to do gzip on it, right? We want to factorize it, and we also want to apply perhaps gzip on factorization. Yeah, because factorization will be plain text, will not be binary. So by doing it binary, you can actually further gain space. So we increase the database scale. Don't ask me exactly how, but imagine for each as we increase the scale means the data the tables become larger and larger and larger. Okay, so as you can see, our gzip factorizations have a compression ratio basically, which is in blue here, right? That is, they actually can improve a bit the factorization we have, but just by a constant factor all the time. This is simply because we actually compress numbers which are written, literals. You compress them into bytes, right? Here in blue, in green, what you see, so the second from the bottom is actually gzip. So gzip here, as you can see, can do some compression, but cannot detect large blocks of repeating data that come over and over again, as it is the case, with our joint dependencies. And the red line, which is at the top, is our factorization, plain factorization, right? So as you can see, we just, hit the roof, which means that we can get, for a scale 32, a compression ratio which goes above 100, right? Which actually shows that gzip cannot actually spot repeating blocks of data that are not, coming one after the other. But if they are, further apart, as it is in a relation, right, then that actually can hurt it. So in practice, we tried with different data sets in the retail business, used by logic blocks analytics, and these are, from our collaborators. And with, for instance, relations with inventory, sales, and so on. And we use this actually for machine learning. And we wanted to understand whether we compress, so how much gain we get. And that would be, if we just join inventory, sensor, and location, which will give us, the input is about 86 million tuples. If we compare our compression versus the compression, well, just listing representation, we get a factor of 26 times, right? So 26 times smaller. If we actually join inventory, sales, clearance, and promotions, we get about 160 times more compact. Well, there are other things for Last.fm where we could get even more. We played also, theoretically to see whether we can get something of the order of 86 million times more compact. But that is just, for academic, well, fun, I would say. In case of, clicks, they don't factorize well, so we cannot really get much. In this case, we get only a factor of 2.7 for the triangle query. But once we go to queries that have clicks but can also be factorized, like a bow tie, which is like having two triangles that touch in one point, then we get something in the order of 5,000 scale factor. Good. So now let me go to the worst case optimal join algorithms, right? So what I discussed so far was the size. Now we understand the size. Can we actually get beyond that? Can we get also to compute it in that time? Yeah, and that has been a very important, elusive, I would say, task. Only in 2012, there was a paper that provided the first worst-case optimal join algorithm for the listing representation. Later on, we came up and provided worst-case optimal join algorithms for the succinct representation, for this factorized representation. So the results here, in terms of time, they mimic essentially the ones for sizes. So in particular, if you want a listing representation, we can get, in the time proportional to n to fractional edge cover number. There is an O tilde there because we avoid we don't write down a logarithmic factor. We use this to sort the input relations before we do the join. Then for caching and without caching, will be the same as the sizes modulo the logarithmic factor, and this they essentially follow the succinctness gap, and they are with respect to data complexity. So where the query is considered fixed. If the query is considered also the size of it is part of the input, then you get an additional quadratic factor in the number of variables and linear factor in the number of relations. Okay? So I will then exemplify how to do such a, how to essentially design and implement such a worst-case optimal join algorithm. So I will consider our running example with the dishes, day, customer, and so on, and imagine that this is the factorization structure you want to use, because you looked up before and you realized that this would give me the best size and the best time. Yeah. So what do? Then you go, for instance, top down. There are approaches that can go also bottom up, but if we go top down, then at the dish, what we do, we look at the relations that actually have the column dish, and we intersect them on the dish. we assume that they are sorted by dish. So this is why the logarithmic factor first, n log n, right? We sort them by dish. And then we can do efficient list intersection of ordered lists. So we intersect them. And for every dish, we then branch out. And then the dish appears also in the order. So we use the dish to do a lookup in the table orders to get the days, yeah, for that dish. So this means that we should sort by dish and then by day. So once we have the dish, the lookup, you can think of binary search, or you can think of having a B plus tree, representation of the data. So then you can do a lookup, and then you can easily get all the days. And then for each dish and day, you can get the customer. So it's like, if the data is sorted, the orders relation will be sorted by dish, day, and customer, then for a particular dish, you get a range of tuples that have that dish. Within that range, you can get ranges for a particular day, and within that, you can get ranges for a particular customer. And then you move like that. So you move in one pass. Okay? And that's the way we do it. And on the other branch, you then look with that dish for items and prices of items. So we wouldn't need to, we can do this in parallel. As you Dominic suggested, then this is, embarrassingly parallelizable in this sense, right? Because at this branching point, you can then use the different branches to do the different things. The kind of parallelization that can be done as well is more subtle. You can do data parallelism as well. That is, you may decide to split the relations into chunks and then have different threads or different machines working on different chunks of the data, right? So that you don't just parallelize the code, but you can also parallelize the data, especially if some data sizes are very, some data sets are very large, such as the previous example with the inventory table. That one has 86 million records. If you break it into pieces and have one thread, one core working on each of them, right? Then you can really parallelize a lot the execution. So, but a very important aspect here is this, that in order to make this efficient and in fact to attain the worst case optimality, you need a very, very fast list intersection, right? So your list intersection has to have this time. So if you have two lists, if you start to intersect them, you have them ordered, then the time taken to intersect them should be proportional to the size, the minimal size of the two lists. So if one list is small, the other one is large, okay? Then you look at the small one. For instance, a possibility is you do a lookup. You iterate over the small, and then you do a lookup in the other. So that's a possibility, right? And if the other one is sorted, then it takes some logarithmic time extra for the binary search. Or you implement this as a hash table, and then you do a lookup in the hash table. This is another possibility, right? But you need that. You need that sort of complexity, which is depending on the minimum size of the lists. Another important thing is that here it didn't appear, but in some cases it may be that several relations talk about the same dish or the same variable, x. Then you have to consider the intersection of all of them at the same time, right? So that you do not first intersect two lists that are very large, get something very large as a result, and then intersect with something very small, because you'll not get optimality. You have to make sure all lists are intersected at the same time, all lists that are relevant for that dish or for that variable x. And that's about it. How can we rephrase this worst case optimal join algorithm? Well, if we strip away the factorization and we just think of it as having just a path as the variable order, this is nothing more than sort merge join, right? Which is a standard algorithm in textbooks, but a bit glorified in the sense that you do multi-way. Yeah, that is, if a variable occurs in several relations, you intersect all those relations on that variable at the same time. Yeah, that is one thing. And another thing is that it should be monolithic. That is, once you get a value for the variable, you move to the next variable. So in the context given by the value for that variable, you now intersect the remaining tables, right? So that is also a very important aspect. But a part of that is just the way it is. So this is what we did. The much acclaimed worst case optimal join algorithm used by logic blocks, for instance, it does not exploit factorization. So this is the one implemented in commercial systems. And it's a special case where the variable order is just a path. And it doesn't exploit dependencies in any way. It's like, the trie. Everything is a trie, and it constructs a trie at the end. If you use factorization, then you can actually get much, much faster. And in particular, if you don't use factorization with our algorithm, you can get exactly the leapfrog trijoin. Good. So in practice, we look at the retailer. So it had about 3 billion values. Last.fm about 5.8 million values. So if you look at the sizes, if we factorize, we get here, for a slightly different data set from the one I mentioned before, 21.4 compression factor. For Last.fm was 1,800 something. So here we have times to do with our approach with the Postgres. But what we wanted is not to compute the factorized representation of the result, but to list the tuples in the result as well. So that is, internally we did factorization, and after that we listed the tuples. So the user experiences the same thing. It's just that internally we use the factorized representation, and then we get 7x and 6x. So a factor of almost an order of magnitude for these small data sets. We looked also at other data sets like housing, for instance, where we have information about prices of houses in different areas, institutions in the same area, and so on and so forth. So we have very many relations that are joined on the zip code. And it turns out that in that case, as we increase the size of the database, the gap between sizes of listing and factorization, they increase to several orders of magnitude, in this case 3 orders of magnitude. But also the times differ by about the same. But in this case, we actually represented the results factorized. So you see, here, if you don't want to represent the results factorized, then you can also get, obviously, much, much higher speedups. But if you want the result to be listed, then obviously you'll pay a price to just list very many possible tuples. But still, it is a good result. Good. So now the second part is on aggregates. Now, this is where it starts to get a bit more interesting, because just joining things is nice, but ultimately boring, right? I mean, yeah, you can join things, right? Can you do something with it, right? And the aggregates are a means to do something with the data, right? You start aggregating over data sets, counting, summing up, producing averages, reports and everything, right? So here is where we start talking about the aggregates. They are important in database query languages, but are also essential for applications. Now, interestingly enough, if we start to, as you'll see, generalize aggregates over joins, so these basic constructs, aggregates and joins, we start now being able to express lots of problems in computer science. And we will actually look at some of these things. The purpose of the second part is to highlight some recent work on aggregate computation with the lowest known computational complexity so far. So that is, we try to inherit the kind of goodies we got out of the factorization for the joins, and see whether we can apply them also to doing aggregates over these joins, factorized joins. And in the third part, we look at how aggregates are essentially a very important building block for doing machine learning, for learning regression models, for instance, right? In a nutshell, the idea there is that the gradients can be expressed, if you want to learn a regression model, can be expressed as such functional aggregate queries, and then can be executed in a very optimized way using the kind of techniques presented here. And we did that, in fact, and it is also, this prototype is actually used also in industry. So first of all, let me see, we will look at aggregates over factorized joins and try to see what kind of aggregates can we do there. Then we will see that we do not need to materialize the factorized joins in order to do aggregates over them. We can then do them on the fly. Then we will generalize these aggregates over joins into functional aggregate queries, and then we will see how we can compute various such functional aggregate queries using an algorithm called the inside-out algorithm, which is a generalization of our algorithm to work over that works over factorized data. In fact, the generalization there, one of the aspects of the generalization comes in the fact that you do not need to use a single sum product semi-ring, a single semi-ring, which is the union Cartesian product, let's say, semi-ring, right? You can use the max product semi-ring, you can use the Boolean semi-ring, and then suddenly other problems in computer science become aggregates over joins and use the same algorithm to solve them. Good. So examples. So this is one of the factorizations I showed you before, right, for our running example, with the dishes and so on and so forth. Now imagine I want to count. What does it mean to count? I want a query that says, count for me the number of records in the result of the query. Okay? So in a listing representation mode, I will just go tuple by tuple, and I will just increment the counter until the very end, and that's it. But here, what we could do is this. Imagine I map every single value of the leaf, or in the inner node, to 1, and the Cartesian product now becomes simply multiplication, and the union becomes simply the summation, right? So I just do that. Then, if I do a bottom-up pass over the factorized join, I get the count. Why is that? Because, for instance, in this case here, when we have multiplication, that stands for the Cartesian product of everything from this side with everything from the other side. So if I go bottom up here, I just say that I have 2 records, 2 tuples on the relation represented by this part of the factorization. On the other side, I have 3. By taking the Cartesian product, I get basically 6 records. I don't need to materialize the 6 records to know that there are 6 records, right? I just know I have 2 on one side, I have 3 on the other side. Let me multiply, I get 6. And that's it, okay? And so every time I see a union now becomes a plus. Every time I see a Cartesian product becomes a multiplication. And if I have sharing, then this means that whatever I computed before, below here will be reused by all the incoming or outgoing edges, okay? And that's about it. So it is clear that I can do such a computation in a bottom-up phase, 1 pass, and that's it. Okay, let me now do something else. Imagine I want something more complicated. I want to do a sum of dish times price. Okay, what does it mean? It means that in a standard setting with listing representation means I go record by record, tuple by tuple in the result, right, of the join, and then I multiply per record dish and price. I take a sum. I take a value of it, and then I basically sum it up over all the records in the result. Now, dish is a categorical variable. It's not really a continuous, right? So how can I possibly sum over it? Well, here I just assume that there is a function f that turns the dish into reals or indicated vectors. If you want to do a one-hot encoding of categorical variables, for instance, right? You say, for instance, I have n, in this case, 2 dishes, and dish burger here means, let's say, 1, 0. Dish hot dog means 0, 1. And that's it. So then I have to extend my interpretation of multiplication from scalars to with scalars, now scalars with indicator vectors, and so on and so forth. So if I do this, I can compute everything. So now dish and price, essentially I say this, because I am interested in the values of dish and price. I don't change them. I leave them the way they are. Or in case of dish, I actually multiply them by, I apply the function f to turn them into reals or some indicator vectors. The price, I leave it as it is, because I want to sum over it. And everything else becomes 1. And I do the very same thing. So I just run up. In one bottom-up pass, I compute after at the end my aggregate. Okay? So I can do this for very many aggregates like this, right? But there is one catch, namely that in this particular case, dish and price, well, at least for the dish sits on top of the other variables, right? Which are, so dish is categorical and sits on top, and price is somewhere at the bottom, right? So in order to do this multiplication, somehow I have to combine values that are for price, which are somewhere here, with values for dish, which are, in this case, somewhere up in the tree. So partially what happens is that for some of the other branches, I have to do counts. Because a dish may appear very many times. Or here, for instance, that dish has been served 2 times. Okay? So that is very important to know, right? So here I don't yet have group by or free variables, right? I just want to sum up over everything. So in case we have group bys, like for instance in this case, if you want to say for every dish give me the price, you then say some price group by dish, okay? And then dish better be on top of the other variables in my variable order, right? Because then I can aggregate everything from below, and for every dish value I will have then an aggregate value, okay? So there is a restriction, so in case we have group by variables, or in this case could be dish, for instance, or they are also called free variables in a query, right? I need to make sure that these free variables sit on top of the other variables in my variable order. Because if it does not, then my factorization is not that easily amenable to computing the group by aggregate, right? Because for instance, if you are here somewhere, and you say I want to group by price. So for every distinct price value, I want to count how many, let's say orders have been out there. Then the same price value may appear very many times for different items and for different dishes, right? So it is not so obvious how you could do that. Better have price at the very top of the variable order, so you iterate over the distinct price values, and for each price value then do a count underneath. And that's the way you can actually accommodate it. So in other words, now if we have group by variables, we have to look at those variable orders that actually are restricted in a way. They have the free variable sitting on top of the other variables, and that's the only assumption we need extra to make here. But that might not give us the best measure, best width. It might not give us the fractional hypertree width of the query. It might give us something which is slightly larger. In other words, if you have group by variables, you may have to pay a higher price to do the query than if you do not have free variable or group by variables. So, and it is also not necessary to compute the factorized join first, right? So, if you would like to compute them without the factorized join, then the factorized join becomes just the trace of the aggregate computation, as I mentioned before, and then we do a factorized computation instead of just representing the factorized join. And I will show you this by an example. I take a path query. So essentially, I have a set of nodes in V1 and a set of nodes in V2, and I have a path of length 1, 2, 3, 4 between them, and I want to check which ones actually would be paired. Whether I can reach some of the nodes in V2 from some of the nodes in V1. Okay? So I construct a variable order here, for instance. In this case, I have, I say, it essentially follows the structure of the hypergraph. I have A, B, C, D, E with the corresponding keys. And if I want to list the result, that will actually take cubic space and time to compute. But if we actually would like to store it factorized, it will just be linear. Yeah? And why is that? Well, because it is cubic because you can actually consider an independent set of variables given by A, C, and E, right? And that gives you already 3 variables which are independent of each other. It has a fractional hypertree width of 1 simply because this is an acyclic query. So if you look at every information on the keys, then each key together with the corresponding node makes up just one relation. Good. So let us compute first the count. So count how many such combinations are between V1 and V2. We said we can do it in linear time. Here we have no free variables. We just count. We basically give back an aggregate value, a number. And we would like to use optimized queries, actually, and not computing the factorization explicitly. So I use the following convention. I assume that every relation is implemented as a function that maps tuples to a value 1. And that could be seen as the multiplicity somehow. That is, that tuple occurs one time. And why is that? Because I will construct perhaps some intermediate relations that will have multiplicities which may be different from 1. Right? We may say, well, I can see this tuple in the result this amount of times. So we start with this factorization, and we go step by step. First of all, we look at it and say, let me actually do a bottom-up approach and start actually eliminating variables from the bottom. I want to eliminate variable a. Right? I want to aggregate it away. So what do? I say, well, this a has v1 has a and e1 has a. If I take the product of the two, right? Because their values would be 1 initially, right? And I sum over all the a's, which are in the domain of the variable a here, right? Then I get a partial result. I get basically a result that tells me for each b how many a's I have. Okay? So I eliminate a. So this is simply variable elimination. And then I go to the next step and I say, let me eliminate also the b. Right? How can I eliminate the b? So I have a previous relation I constructed u1, which is over the b, which gives me some value. I mean, how many a's would be for that for each b. And now I join that with e2, with that edge. Yeah? And I aggregate away b. Now I essentially get how many pairs AB I get for every C. I do the very same thing for the other branch, okay, because I still have a branch with E, D, and C. I do the same. I aggregate away, until I end up with just a single variable left, variable C, which was at the root. Right? What do I do now with it? Well, I simply, multiply the, here we get, how many pairs A, B I get for a given C. And on the other side, I have in U4, I get how many pairs D, E I have for a given C. I multiply this, and then I aggregate away over C values. And then I get the final result, the count. Okay? So that's the way you can do the factorized computation without having to explicitly represent a factorized join. Okay? So that's the second approach by which you can use factorization in a relational setting without having to store a graph data representation. Now, if you look at this, what I really did was this. I started with such an expression, which is at the top here, where I said sum over A, sum over B, sum over C, sum over D, sum over E, right? And then you take a product of all the constraints you have in your database. Yeah? So this means that for every satisfying assignment of these guys, for every tuple A, B, C, D, E that satisfies all these guys, you count it as 1, right? Because that will be is 1 multiplied by 1 multiplied by 1. So everything here will be 1 for such a tuple. And then you sum over them, over all those ones. Okay? And that gives you the count. Alternatively, you push some of the sums past the multiplication. And that is what we did with our factorization anyway, right? So we push the sum over A here closer to A, right? So that you only push it closer to those functions that talk about A. Similarly for E. And after that, whatever is left here, you push it into the other multiplication with E3, and then you aggregate away D, and so on and so forth. So what I did now was I took those step-by-step computations I showed you before and plugged them in instead of materializing them, explicitly. So that's basically what what we could call a factorized aggregate computation over the join, right? You try to push the aggregates past the join as much as you can. Yeah. It sounds very simple, but there is a wrinkle which we have to consider. Namely, in case we have cycles, sometimes this approach does not work right away, right out of the box. We have to do a little bit more work, and I will show you in a second. But first, is this practical in practice? So what I did is this. We used the retailer data set, also an excerpt of it, and of 70 million records, but also 86 million. The input, and then we benchmarked, okay, how much time does Postgres need to compute this stuff? This is an open source software. We can, compare against it without, having any sort of problems with, commercial systems. So this is why we do it with this. We might not be allowed to show, performance numbers with a real, commercial system. So, and this takes about 50 seconds here and about 216 seconds there, right? to just do the join. But instead, what we did is this. We said, let's compute the join, but together also a number of aggregates together with the join and see what would be the time. So in this case, we compute the join together with 595 scalar aggregates and 2,400 something group by aggregates. So very many aggregates together. Why did we ever think of computing something like that? And what are these aggregates? Well, it turns out, as we will discuss in part 3, these are the aggregates we derive from, essentially the covariance matrix we use to learn a model, a regression model. In this case, a linear regression model. So this would be the amount of aggregates we need to compute. So in this case, we said, okay, let me compute all these aggregates together over the join. And then, as you can see, it takes actually half the time to compute the join only with Postgres, right? If you'd actually use Postgres to do also the aggregates, one way, the naive way is to do one aggregate after the other, and then that actually takes a lot of time. So you just materialize the join, and then you compute the aggregates on top, right? Okay, but that will still be a long time. Now, if you move to the full data set, then the number of aggregates you have to compute would be in the order of 145,000, right? Group by aggregates, which is a very large number of aggregates. But still, it takes us about 380 seconds to do that, together with the join, whereas for Postgres, it takes about 216 seconds to only compute the join, to give a rough impression of what's going on. And here, we didn't activate various things. So for instance, we just used one core on one commodity machine. We don't parallelize at this stage, okay? So we also looked at computing a different number of aggregates together with the join. And that second part here is actually for computing a polynomial regression model degree 2. And that gives us, more group by aggregates because we have a lot of categorical features that interact between each other. And then we get something in the order of 742,000 aggregates. Here we get about 37 million aggregates. And as you can see, the time is actually still doable, on one commodity machine, right? Postgres cannot compute this sort of stuff for very many reasons. There are various limitations here. One is obviously time. If you leave it, crunch numbers for a day, 24 hours, and still doesn't finish, then you have to stop it. Otherwise, you just waste energy. The second thing is, however, that you cannot actually compute. Let's say you compute the join, and then you say, let me compute all the aggregates in one query. You cannot do that because Postgres can only compute tables with at most 1,066 or something like that columns. That's it. You cannot put 742,000, columns in a table. Yeah, and that's a strong limitation here, right? So okay, so that's to give you an impression of whether factorization can actually be useful, and I think it is. Good. So this is a topic which I call functional aggregate queries, which, in interest of time, I will have to skip, sadly, unless you want it. So who would like to hear about this?
How long does it take?
Okay, so let me then go over it. Okay, so it's fast.
I don't believe that was the question.
Okay, so so the idea with a functional aggregate query is this: that imagine that the kind of queries we've seen before, right? With products of these functions, right? And then summations on top, where we aggregate away a variable, right? We go over the domain of a variable and we aggregate it away, okay? So this sum product all the time. The thing is, however, that this sum and product may mean different things in different settings, right? And that is the power of the semi-ring which we use, right, to capture the computation. So notation, we use xi, the capital X, for variables. The small x would be the values in the discrete domain. So we use only discrete domains in this talk. And then if we have a tuple, then it is in a bold x, right? The tuple x1 to xn would be the, it's a value in the product of the domains, right? And then if we have S, which is a subset of, from 1 to n, it means essentially we want to refer to a tuple of values over the variables x1 to xs, and that's it, right? So for instance, x258 means we have a value x2, x5, x8 that belong to the domain x2, domain x5, domain x8. Good. So an FAQ expression does exactly this. You give us input functions. If you feel more comfortable, you can call them factors, right? In PGMs and other things, right? You give them as input. They are over some of the variables. And the FAQ expression states a product of these factors, okay? And then some aggregates. That can be max, product, sum, over some of these domains, right? For instance, here it is a maximum over the possible values that the variable x4 can take. This is a product over the possible values that x2 can take. This is a sum, right, over the possible values for the variable x1. And what we produce at the end, we produce a function over the variable x3. Okay? So that's the thing. So with such an FAQ expression, we associate a hypergraph. Now, the variables become the nodes again, right? And these functions we give as input, they will play the role of these hyperedges, right? For instance, we have a hyperedge over x1, x4 simply because we have a function, a factor, that goes over x1, x4, and so on and so forth. And in this particular case, for instance, our variables will be 1, 2, 3, 4, or x1, x2 up to x4 to make it simpler. And the hyperedges will be over 1, x1, x4, over x1, x3, to x2, x3, and so on and so forth. Okay? So that's the kind of formalism we use. And right. And all functions will have the same range. So all functions will actually map some values from some domain to some values from the same domain D, right? So that we can multiply the values produced by the different functions, right? So all of them will be of this form. And this domain D could be, positive numbers, could be the true, false, could be 0, 1, could be, subsets of a given set, and so on and so forth. Good. So let me actually, right. So okay. So I think I should explain this as well. We write an expression, this formalism, as follows. We say, we apply, well, we have some variables in the head. And here, with this, we mean from 1 to f, right? So we have f free variables. And then we express it as follows. At the very end, we have a product over all our factors or functions. So this stands for a product. Okay? So that is, we look at all the hyperedges. And for each hyperedge, you look at the actual function for that hyperedge. And after that, for every variable which is not free, we aggregate it away using such operators. Okay? And these operators may either form a semi-ring with the product, or maybe just the product. Right? If you say, it is as if you say, I take an AND over all the possible values in the domain, right, for that particular variable. Otherwise, it can be a plus, for instance. Yeah. So why a semi-ring? Well, in the semi-ring, we have two operations. We have the plus, and we have the times, right? The plus and the times. And we have the following properties. We have the additive identity. So there is a neutral element, 0, in the domain. So if we add it to another element, we keep the same element. Then we have multiplicative identity. That we call it as a 1. And if we multiply it with another element, we get that element back. And then we have annihilation by 0, which is, if you multiply 0 with anything, we get 0. And we get the distributivity law, which is, if we have A times B plus A times C, it is the same as A times B plus C, which is exactly, the core of our factorization. So we need that property in our processing, right? So we can actually use factorization, and that fits very well with the semi-ring idea. So common examples are the Boolean semi-ring, for instance, where the domain would be just true, false. Then OR will be disjunction, AND will be conjunction. Then the sum product over, let's say, the reals with just the normal plus and times. And then the max product semi-ring you could use where the plus, in fact, is a max now, right? You take the maximum. And it could be the set semi-ring where you take the power set of all, the power set of a particular set U, and then you can use a union and intersect as operations. Okay? So with that, we can define the sum product problem, which is given a commutative semi-ring, we want to compute this function. And this function, again, you take the product over all the hyperedges, right? You look at the factors over the hyperedges, and then you aggregate away all the variables which are bound, which are basically only existing here. They are not in the head of the query. And these are the free variables which are in the head. Yeah? So this sum product has been around for a while. Rina Dechter, for instance, had it in an AI, artificial intelligence journal a while back. It has been also called the marginalized product function, MPF, right, with AG and McEllis in the transactions on information theory in 2000, right? But could be generalized, actually, So that was the catch of this work. There are very many examples of the sum product semi-ring. So you can phrase in that language problems like if you use the Boolean semi-ring, then you can get constraint satisfaction problem, the CSPs. You can get Boolean conjunctive query evaluation. You can get SAT. You can get K-colorability, and so on. If we actually take the union, and intersection, as we have seen, you can get conjunctive query evaluation. If you take plus and times over the reals, you can express the permanent, the DFT, inference in graphical models, and so on and so forth. Even aggregates in databases, as we have seen before. And if you take the max product semi-ring, you can get the maximum a posteriori queries in probabilistic graphical models. All of them can be phrased with that, and now you can use a single algorithm, which is exactly it's in the spirit the same as the algorithm I showed you before for the few examples, on doing aggregates, and that would just work out as well for all these problems. Well, what is the gain? Well, there are a couple of gains here. One is that people actually understood some of these problems in the context of, for instance, tree width and tree decompositions, but not hypertree decompositions, and let alone not fractional hypertree decompositions, where the fractional part plays a major role. So now you can actually get much, much lower complexities because of that. Okay? And that you can now apply uniformly across the whole thing. So I have a couple of examples of the sum product semi-ring in action. One is the Boolean conjunctive query. So here we have a query, a Boolean query that has a set of relational symbols. Here you have, for instance, this one. You say there exists x1 up to xn such that you have a conjunction holding between, some relational atoms. Okay? So you say R of, AB and R of BC and R of AC. That would be the triangle query. But then you say n exists A and exists B and exists C. So that is, you are just interested to know whether there is at least one triangle, in your database. You're not interested in listing all the possible triangles. And that's the Boolean case. Well, how to encode it as a functional aggregate query? For every relation symbol, you actually construct a factor or function, right? That goes over the corresponding variables. You take an AND over all the possible factors, and then you take a disjunction over all the possible assignments of the variables. And that's it, you get it. Okay? So what about the matrix chain multiplication? Well, if you have, let's say, matrices A1 to AN, which are over a field F, and each has dimension pi times pi plus 1, what do? Well, the FAQ encoding is this, right? You consider every matrix encoded as a binary relation, okay? With two variables, one variable ranging over pi from 1 to pi, so that you can address the rows. The other variable goes over the columns, and the value at a particular intersection of row and column would be an element in a field F. Okay, and that is what you do. So by this, you define in fact a factor for every single matrix. And after that, the problem of matrix chain multiplication is simply this aggregate. You take the product of all your factors for all the matrices, and then you aggregate away all the variables except for the first and the last, right? Because you would like at the end to produce a matrix which is of size p1 times pn plus 1. And everything else is actually, inside. And now you can apply an algorithm that looks at how to push these aggregates, past the products. Queries in graphical models, for instance, well, in this case, we can consider a discrete and direct graphical model represented by a hypergraph. And the hypergraph has edges which are n discrete random variables, and a factor is defined over some of these variables, right? And will give you back an element in some weight, some positive value. Okay? So the FAQ expression to compute the marginal maximum a posteriori estimate, for instance, would be this. You take the product of all the factors, and then you maximize over every variable in there, well, which is not free, right? So you like the MAP to construct it for every possible tuple over the free variables, you want to construct the MAP. So this maximum essentially says I will have to choose the right value in here and in there that would maximize this product. Yeah? And that's the way you do it. If you want to actually compute the marginal distribution of variables x1 to xf, that's instead of the max, here you have the sum. You sum over the values of the random variables, and inside there you have the product of all the factors. Now, for conditional distributions, right, what you have to do, well, let's say if you have P of xa given xb, right, then xb are fixed to some constants. You look up at the variables that correspond to xb, right, and you set them to those constants in here, right? And then you compute your expression. And then you get the conditional. Okay, so let me actually show you an example of FAQ computation using this algorithm inside out. In contrast to the one I showed you before, they achieve essentially the same complexity, but the previous one, we came up with this top-down. This one goes bottom-up. So eliminates variables from the bottom somehow. Okay, so this expression here does the following. Says, well, I have 1, 2, 3, 4, 5. I have 5 factors over different variables. I multiply them, and I want to aggregate away from x3 to, well, x3, x5, x6, x7, x8, and I want to keep x1, x2, x4. Yeah? So what I do, I construct a variable order, for instance, right? I put the keys and everything. Yeah? And now I start aggregating from below. So first of all, let me actually contemplate what would be the complexity if we do it optimized and unoptimized. If we don't do it, we don't optimize at all. That is, we first compute the product of these factors, and after that we aggregate away things. Then, if you think a bit, you'll get the fractional edge cover number 4. That is, it will get something like n to the power of 4, right? If you actually want to solve it with the factorizations without caching, you get something like quadratic. But with caching, it will be just linear. So you can do this in linear time. So this is because in this particular case, so the fractional hypertree width of this variable order is 1. And if you look at the free variables x1, x2, x4, they actually sit on top of the other variables. That is for, you can aggregate away this, you can aggregate this, and that. And at the end, you can stay with the factorized representation of this guy. And hanging off every x1 value will be some aggregates, right? And that's the way you can do it. If you want actually to compute, to list the combinations x1, x2, x4, you may get quadratic. But that's still okay. It's much better than actually to the power of 4, right? So how can we do this? We start with this, right? So initially, we just assume everything is, we have a product initially, and after that we aggregate away. But then we say, okay, let me look at x3. And I want to aggregate away x3. So I look at this expression psi1, right? And I push the x3, summation over x3 inside, okay? And I aggregate it away. So I construct a new factor, which is only over x1, x2. And I can do this in linear time, okay? And then, as you can see, right, if you look at the variable order, we don't have x3 anymore because we aggregate it away. The second thing now is, we like, for instance, to aggregate away x1. Oh, actually, we want to aggregate away x8, sorry. So we look at x8. This is the relation that talks about x8. We aggregate it away, and we only keep x6. right? And we replace this by x7, right? So we can do this also in linear time. Now we look at x5, x7. We can aggregate away x7, and we only keep x5. This can be also done in linear time. And then we look at x6. x6, is used by this blue hyperage, but also by this greenish hyperage. So we have a product of two factors, psi7 and psi3. Right? Psi7 was the one we constructed before. And that is because both of them have x6. We aggregate it away also in linear time. At the end, we want to aggregate away x5. Now we have a product of three factors that talk about x5. We can do this also in linear time. And we end up with a product of two factors that only talk about the three variables. We can stop here and then we get a factorized representation of the result. Or we can, in fact, multiply it further and then we get quadratic. Okay? And that's the thing. Now, let me actually show you a more interesting case. This is the case of a bow-tie query. So we have, in fact, two triangles. Right? We have a triangle on that side and a triangle on this side, and they meet in one point, the triangles. Okay? So how can we do this? Now, we know that each branch corresponds to a triangle, and we know that we cannot really factorize well triangles. But the two triangles can be kept apart. And here is where we can gain. So if we look at this bow-tie query, and we look at what would be the size and time to compute, in fact, the listing representation of it, then the fractional edge cover number would be 2.5. So it will take n to 2.5 to do it. But if you actually want to keep it factorized, it's just n to 1.5. Why? Because it's 1.5 on one side, 1.5 on the other side, right? Which is what we discussed for the triangle query. And we keep them separated. Okay? And we want at the end to have, as you can see, the possible values for x1. Right? So x1 is actually a free variable. So for each x1 value we want to compute, in this case, we want to aggregate away all other variables, and we want to count, right? How many times x1 would appear in the result. So how can we do it? Well, let me actually try to remove x3. The trouble with removing x3 is this. x3 is used in two relations. In one case is x2, x3. The other one is x3, x1. But there are additional constraints on the variables appearing here. If I would just aggregate away x3 by joining psi2 and psi3, I can get quadratic time. But I need to add additional constraints to the problem. These are constraints that go over x1 and x2. In particular, I actually have to do the multiplication with psi1 as well. And this is actually, I call it psi1 prime, because it doesn't really, how can I say, it is an indicator projection code. That is, all the values in here are like the values in psi1 itself, but they are mapped to 1. So they do not carry with them the actual values they actually might actually have in the input. I'm only interested in the existence of the combination of an x1 with x2, because I use this only as a constraint on the additional product I have in blue here. And now I use also additional constraints. Let's say, I have x1 appearing somewhere else. Let me put it in here as well. Why? Because it may give us a smaller domain for the possible x1 values. So it may actually make it faster for me to evaluate this. So it is only now that I can actually aggregate away x3. So I have to do the product of these guys in here, and then I aggregate away x3. And this is what I do, right? I construct a factor over x1 and x2 alone. I put it in there, and I know it takes time, which is n to 1.5. And I do something similar for the other branch, obviously. But before that, we can also aggregate away x2. We can aggregate away x2 by actually, taking everything that talks about x2 and all other variables that appear together with x2 in factors. So then I aggregate away x2. And then it takes just linear time. And then I do the other bits that take n to 1.5. And O to n, and that's it, right? So overall, the complexity of solving this would be the maximum of these complexities, which is n to 1.5, instead of being quadratic, yeah? Or to the power of 2.5, which would be the listing case. Good.